has the right pronunciation for his name.
Okay, we're pleased to have Fraydoun Rezakhanlou from Berkeley to give a talk on stochastic twist maps and symplectic diffusion.
Thanks for introduction and thanks for saying my name correctly. It doesn't happen very frequently.
The first time I wrote your name with Fraydoun in the
There are like 100 ways of writing that. You know, in Persian, of course, there is only one way to write it. But if you
Alvaro was objecting me that that's not the right thing. I said, no, I know that that's the right thing.
So it's a pleasure to be here. I spent a year here 20 years ago as a postdoc, then you can tell how old I am. And it's really nice to be back here. So I want to kind of discuss symplectic property for random maps that are either symplectic or nearly symplectic. But first I have to kind of give you some motivation. Why should I care about that map? And that has to do with a result that I learned from paper by Constantin and Iyer for Navier-Stokes Equation, and try to understand that in the language of symplectic geometry. And that led to this concept of symplectic diffusions. So to kind of motivate the problem that I'm interested in, let me simply remind you that, of course, if you have a symplectic ODE, if you have a Hamiltonian system, or using Q and P for the position and momentum, if you have a system that looks like this, and if I denote its flow by phi t, then of course we know that phi t is a symplectic transformation, which means that if gamma is a curve, closed curve, and if you look at this integral, then this is the same as evaluating this integral over the original curve. Or if you have a surface gamma, and if you look at this 2,4, some kind of the sum of projected areas, and you know, if you keep track of the sign, and then this integral is also preserved under the flow. Okay, and that's the reason we care about symplectic transformation, because the flow of a Hamiltonian system has this property. Now, let's make an observation. Maybe I try to find solutions of this Hamiltonian system that happen to lie on a graph of a function. So look for solutions. P equals to u of qtt. So u is a vector value function. Okay. If such a function can be found, then this system, of course, reduces to a smaller system, because all I have to do is now solving this ODE. However, such a function would exist if this condition is compatible with this condition. And of course, when you differentiate this, you get that the derivative of P is uq, the derivative of q, which is hp, plus ut, and these two would match if u satisfies this differential equation. U is differential with respect to q. That's a matrix times this vector. So if u satisfies this differential equation, then of course such a reduction is possible. In particular, if your Hamiltonian is the classical Hamiltonian, namely is given by 1/2 of p squared plus a suitable potential, uppercase P qt, then this PDE becomes ut plus the derivative of u times u plus the gradient of p qt. Oh, you need more light? Ah, much better. Okay, for classical Hamiltonian, this is nothing other than the Euler equation. And let's see, what does it mean for this property when you translate it here? Well, for the curve gamma that I'm going to choose here, I'm going to choose a curve that lies on the graph of u. In other words, you take a curve in q space and use u to produce the other coordinate. So if eta is a q curve, meaning a curve in q space, then that equation, this property, is nothing other than, and okay, so you see eta mapping by this flow. To figure out what that map is, I need to introduce another flow, but first let me simply write it as x of gamma and put here u qt dq equals to u q0 dq gamma, where x is the flow of this ODE, which in this case, for this particular Hamiltonian, is nothing other than dq dt equals uqt. So what we learn is that if you take an arbitrary closed curve gamma, and if you take the flow of this, denote the flow by x, so this is, the other way to put it is that x differential respect to time equals u composed with x. So if x is the flow of u, then this integral is preserved, and this is nothing but Kelvin circulation formula. So in summary, what we learn in fluid mechanics, that circulation formula is nothing but the conservation of the one form or two form, which was known to Poincare. And what happens to this formulation? Well, first, before I go on, I can get rid of gamma and write an equation that involves u only. And just by putting x here, differentiating, let me call this formula 1. 1 is equivalent to saying that if I kind of differentiate this and put the derivative on here, becomes du dx star times u at time t equals to the initial condition that from now on I denoted by u0. And of course, since this is true only for closed curves, I'm going to add here some gradient of some function that I maybe denoted by zeta. And if A denotes x inverse, then I can move this to the other side, and what I get is that uqt equals to dA star composed with x, u0. Actually, I made a mistake here. I think here I put the gamma here, so I have to compose this by x. Then this is correct, because here I'm kind of substituting for q x of that curve, so you're composing with x. So the other way to write this is that dA star times the initial condition evaluated at. So I'm kind of putting the inverse here. Let me see. So first, I'm multiplying by the inverse of this. Everybody would have x. Then I get rid of x by putting a here. So basically, I end up with dA star u0 composed with A plus a suitable gradient, which, you know, it turns out to be, again, a gradient when you do everything. And the other way to put this, you can get rid of this term by projecting this onto its divergence-free part. So the whole equation becomes uqt equals to P of dA star u0 composed with A, where P is Leray-Hodge projection onto its divergence-free part. Okay, so let me put this in a box. This formula, of course, should be coupled by the fact that the divergence of u equals 0, as we have it for, well, actually, this is already divergence-free because of the projection, but this should be coupled by the fact that A is related to u by the following formula. The derivative of x equals u or x, and A is x inverse. So this is known as Weber formulation of Euler equation. And this is equivalent to Euler equation. Which is ut plus uq u plus gradient p equals 0, and the divergence of u equals 0. So what's the difference? This is kind of more analytical, and this has some geometric flavor, which basically is equivalent to saying that something is invariant under the flow of the velocity field u. You can get rid of all this projection part if you go to this formulation. In this formulation, you can, this two form evaluated as a pair of vectors, you can kind of restrict those vectors to those that are tangent to the graph of u. So if I call this formula 2, for example, so 2 means that the 2 form omega v1 v2 equals to j v1 v2 with j equals 0, identity minus identity 0, is invariant for phi t. And if we choose v1, so this is a vector that has q part and p part. For q part, I'm going to choose an arbitrary vector. And for p part, since the vector is supposed to be tangent to the graph of u, I'm going to take du times w1, and you do likewise for v2. If you choose these for this invariance, then 2 means, so I'm going to express that for those surfaces that lie in the q space and use the flow of the vector field u. And if you use that, then all that boils down to saying that, so when you multiply it out, the antisymmetric part of du shows up. And since you're in dimension, if you're in dimension 3, then you can use the curl to represent it. That would be multiplication by the curl. So all that, when you translate it, becomes nothing other than saying then that means that if psi is the curl of u, then psi composed with x times dx times w1 dotted dx w2, two arbitrary vectors. This is basically this side equals to the other side at time t equals 0, which is nothing other than saying then the curl initially times w1 dotted with w2. These two are equal. And note that this is the triple product of 3 vectors. This is basically the volume form. And since the vector field is divergence free, then this guy is volume preserving, which means that if I multiply these three vectors by dx, I would get the same thing. So the left-hand side also equals to dx psi 0 times dx w1 dx w2, because dx is volume preserving. And if you compare the two, you learn that psi ox, the curl mapped by the flow at time t, equals to dx times curl initially. So if you add to this the fact that ux is the flow of u, and psi is the curl of u, this turns out to be a new formulation of Euler that is also equivalent to Euler equation. And the advantage of this formulation is that it doesn't involve any projection. In fact, you can differentiate both sides with respect to time and derive a differential equation which is the analog of this, but now for psi. By differentiation, it's not hard to see that this is equivalent to saying that psi differential with respect to time plus dx plus d psi times u equals to du times psi. So this is an alternative formulation of Euler equation. They are all equivalent to each other. Okay. So far, these are simple observations. The fact that these are equivalent, these formulations are equivalent to Euler equation, I learned that from a paper of Iyer-Constantin, and then later there was a work that kind of extended this formula and the previous formula, or the circulation formula for Navier-Stokes equation. And since this simple result for Hamiltonian system implies that, then you may wonder whether there is the kind of random analog of this story for diffusions that you can use to derive their formula for the circulation. So I get to that eventually. But so far, let me just emphasize that one way to understand Euler equation is this geometric formula, which is nothing other than the fact that the the standard two form is invariant for a Hamiltonian system in this particular case, when the Hamiltonian function is of that particular form. Okay, so let me continue. So summary, let me summarize the situation. Euler is equivalent to Weber formula, which is more or less the fact that the standard two form is invariant. For in a particular situation. So the next goal, Navier-Stokes. So this is kind of like a Weber type formula. And this is the work of Constantin Iyer. Now the question is whether we can find some kind of symplectic way of understanding this formula and say more. And to say more. And I explain what I mean by saying more. Okay. So now I want to understand whether a diffusion could be symplectic. What do I mean by that? Okay, previously we looked at the equation of this form. let's say V0 is a suitable vector field. Okay? So if you give me an ODE, the flow would be symplectic with respect to two form if certain conditions are satisfied. But I want to perturb this by some white noise. I want to add to this so here V0, V1, Vk, these are vector fields. And B1, Bk, these are standard one-dimensional Brownian motions. A solution to this equation is called a diffusion. This would be the drift, and these are used to calculate the diffusion coefficient. However, this doesn't make sense the way I wrote it, because Brownian motion is not differentiable. The derivative of this is known as white noise. So it doesn't make sense as a function because it's the derivative of a function that is not differentiable at all. However, we know how to make sense of this differential equation without worrying about the definition, the meaning of this term. Namely, instead, we write it like this. And Ito was the one who made sense of this. Before the diffusion were known, before Ito, but Levy had this idea that there must be a probabilistic way of understanding the diffusion by saying a diffusion is basically locally looks like an ODE plus a Brownian motion that has certain diffusion coefficient. That was the idea of Levy, and Ito was the first who made sense of it mathematically. In fact, how you make sense of this still doesn't make sense, but the best way to understand it is to interpret this as this expression, which now boils down to make sense of stochastic integrals. If I make sense of this stochastic integration, so now I have to integrate this, then I have a better chance to make sense of it. After all, without this, the integral is a Brownian motion. I got rid of the derivative, I know how to make sense of it, so I have a chance to make sense of this. And once you make sense of it, then it's not hard to prove the existence of solution under some standard conditions. And just the way you prove the existence of solution, existence and uniqueness in the case of ODEs. However, there's some subtlety to make sense of this. To make sense of this, so in general, let's see how I can make sense of Vx, for example. X is a process which is as bad as Brownian motion, because after all, if somebody solves this equation should be as bad as Brownian motion. So you want to make sense of this. In fact, you may wonder whether you can approximate this just the way you approximate a Riemann-Stieltjes integral, namely by saying that I can approximate this by choose a grid for the interval st and use that grid to make this approximation. Perhaps I make sense of this integral by this approximation. However, there's some subtlety when you make sense of this integration. For example, if the function b were a nice function, smooth function, or even a function of bounded variation, it wouldn't matter what you choose here. You can put here any number between tj and tj plus 1. So this is a grid you're using for your approximation. And wouldn't matter what you pick between these 2 points and put it there. But since Brownian motion is not a finite variation, here is very sensitive what you select here. If you select the first, the smallest point in the interval, you get Ito formula. However, sometimes you're better off to choose a different time between tj and tj plus 1. In fact, sometimes you want to be fair, namely you want to choose this guy instead. The answer, however, the result you get by such an approximation is drastically different from the one you got by choosing the first point of the interval. So this is one possibility, this is another possibility, or you can choose the last point tj plus 1. That's a third possibility. They all lead to a different expression, different integrals. If you choose it this way, it's called Stratonovich integral. If you choose it this way, it's Ito integral. So this is Stratonovich. and this is Ito. So why should I bother with one way or other? Well, if you choose Ito, the advantage is certain processes you can get out of the diffusion that happen to be martingales. So I suppose the audience I'm dealing with today, they don't know, maybe they're not very comfortable with martingales, but martingales are very nice processes to deal with. And I explained why martingales are important, because later I'm going to produce a lot of martingales associated with the Navier-Stokes equation. But the advantage of Ito is that automatically it produces martingales, and you can take advantage of it. So what's the advantage of Stratonovich? The advantage of Stratonovich is that if you want to do differential geometry, use a Stratonovich, because the usual rules of calculus apply. In chain rule, Newton's rule for composition of two functions when you differentiate it applies. That wouldn't be the case in Ito calculus. And since I'm going to discuss some geometric property of diffusion, is preferred to first use the Stratonovich and in the end translate it back to Ito. Okay? So the notation that we use is this. So if I want to make sense of an integral of this form, when two processes are involved, if I do approximation a la Stratonovich, I use a circle in between. That's the standard notation. Stratonovich. But if I'm interested in using Ito, there is no circle. After all, Ito was the one who defined such an integral. And what's the relationship between two? Well, it's easy to figure out what relationship is when you use these differences. You know, if you look at the difference of these two, then you would have a difference of v's times the differences of b's. And whatever you get, you pass to the limit and create a notation for it. The limit would be denoted by some kind of covariance of these processes. That's the notation we use. So we have a way of relating Stratonovich to Ito. Whenever convenient, I can switch from one to the other. And we know how to calculate these. So that's the relationship. Now I'm ready to say the theorem about diffusions. But the notation that I'm going to use would be a Stratonovich, because all formulas would be simpler. In the end, however, I need to have martingales, then I switch back to Ito. Okay? So let's start with a claim. Suppose X, this random process, solves the stochastic differential equation a la Stratonovich of the form. I guess I'm getting tired. Stratonovich, if it's correct. Stratonovich. So it looks like this. V0x, maybe I simply write V0, dt plus sum j from 1 to k, vk circle dbj. So suppose x solves this stochastic differential equation. It turns out that if v's are nice, this solution, which is random, produces a flow. The flow would be random. So, and suppose phi tx is the corresponding random flow. So my solution is random. If you do it carefully, then in fact you can produce a flow. That flow would be random. And now let's take a deterministic form, alpha 0, and evolve it by this flow. Let alpha 0 be a form, and set alpha t to be this flow acting on alpha 0. So now my form, so I have a path of forms which is now random. And I want to differentiate this. Differentiate with respect to time. So here I better choose a different notation for time differentiation. This is not the usual d that you use acting on forms. This is the stochastic differentiation, time differentiation. So maybe I use d bar. This is the stochastic time differentiation. As opposed to exterior differentiation, you do it on forms. This, use this notation. I want to differentiate alpha t to see what I get. What you get is going to be L, the derivative in the direction of the drift of the form alpha t dt. This is again time differentiation, plus sum j from 1 to k, L vj alpha t circle Brownian motion. Okay, so these are all, the usual time differentiation. Okay, so this is the analog of Cartan's formula. If all these vj's go away, then this is nothing but the formula you have for differentiation forms. However, this is not convenient for producing martingales, so I want to tell you how you can switch back to Ito language and get rid of this circle. Equivalently, d bar alpha t would be, I'm going to write a new operator which depends on all the vector fields involved in this problem of alpha t dt plus sum j from 1 to k L vj alpha t Brownian motion, but now there is no circle. I have to tell you what this operator is. This operator where A of these vector fields is L of V0, so that's the previous drift you had in the beginning, but you have to correct it. And you know this 1/2 and all the correlation that shows up here? So that would kind of tell you what kind of correction you are going to have. The correction would be sum j from 1 to k, the Lie derivative squared, applied twice on your form. That's the formula you get. It's kind of more or less standard calculation in stochastic differentiation, so it's not hard to derive these formulas. But let me tell you some consequences of this. So now I can answer various questions you can ask for the flow of a diffusion. The first question to ask is that under what conditions a flow of a diffusion is symplectic with respect to a two form with probability 1. So question 1, for what V0, V1, Vk, the first question. Perhaps I should say, given a two form, symplectic two form, alpha 0, so you give me a two form, exact, non-degenerate two form, and you give me these vector fields, and I'm wondering for what vector fields I would produce a flow that with probability 1 is symplectic. Phi t is symplectic. Okay, answer. You see, if you go back to this formula and you want to know, basically the question is under what condition this derivative would yield 0. The derivative, time derivative, is 0. First, to have 0, all the Brownian motion should not be there because they will tell you that things are fluctuating. So all these coefficients must vanish. These coefficients vanishing means all these Vj's must be symplectic vector fields. For example, you can choose some Hamiltonian vector fields. In this case, it's the same if I'm in Euclidean setting. And then after that, all Vj's for j bigger than 1 would be symplectic. Then you go back here, so this part vanishes. Then you say V0 must be symplectic. So the answer is all V0, V1, Vk must be symplectic. With respect to alpha 0. However, so all the coefficients of the noise and the original drift must be all symplectic. However, in practice, yes?
If all the Vj are not symplectic, it's possible to have compensation in the sum there?
No.
Zero?
No.
It's not possible?
there are ways to, when you do the calculation in reality, the noise cannot cancel the drift. In a stochastic sense, that's never the case. Because we can calculate the second moment of this, and then these things are squared, then you get dt here, and there's no way to have such a cancellation. The drift, noise, two different things. They don't mix up with each other. Okay? So that's why that's the answer. That's the necessary and sufficient condition. However, I want to formulate a weaker condition which is relevant for many purposes. And you see, you don't want, it's too much to ask for a diffusion to be symplectic. What you want to ask is that this term goes away. You want the drift goes away so that this guy becomes an stochastic integrals. All stochastic integrals are the so-called Martingales. These are very nice processes. They are fluctuating, but in average they are zero. So it's a simpler, a kind of weaker question to ask is that under what condition only expected value of this random process of forms, that expected value doesn't change with time. And that's equivalent to say under what condition this alpha t is a martingale in time. And then the answer is only this particular summation acting on alpha 0 must vanish. So the second question is when alpha t, which is phi t star alpha 0, is a martingale. In particular, if you take the expected value of alpha t, so get rid of the randomness, then it doesn't change with time. So answer. Now instead, you need LV0 plus, well, whatever A is, A V0 V1 Vk of alpha 0 must vanish. And I'm going to discuss two scenarios that will tell you how systematically you can produce such diffusions. Such diffusions, they don't produce a flow that is symplectic, but is in some average sense is only symplectic. And these are the ones you encounter for some examples of interest, especially Navier-Stokes equation you would encounter. Okay, so let me give you two ways of constructing such symplectic diffusions. I call such a diffusion a symplectic diffusion, perhaps. The one that is weakly symplectic. Okay, examples. Okay, one way to produce a symplectic diffusion is that you give me the vector fields that multiply the noise, and you want to choose V0 for which the whole thing is symplectic. So given V1, V2, Vk. So don't forget that the equation looks like this. dx equals V0 dt plus sum j from 1 to k. So these are the coefficient vector field that you see multiplying the Brownian motion with a circle because I'm using Stratonovich formulation. Otherwise, you have to modify V0. So given this, we can select. There is a unique way of selecting V0 so that the whole thing is symplectic in this weaker sense. We can select V0 so that phi t is symplectic in weaker sense. And it's easy to figure out what that condition is. So these are given, and you want to figure out how play with V0. In fact, you can kind of make it Hamiltonian. In fact, for example, your V0 is going to be the sum of two parts. The first part is a Hamiltonian vector field, for example, or symplectic vector field with I V0 bar alpha 0 equals to d of this is 0, right, for example. So, that means V0, choose V0 part. So, you see, previously, for having the flow symplectic, all V0, V1, etc., must be symplectic. But here, you can choose V1, V2, Vk arbitrary and modify V0 so that the whole thing is symplectic in a weaker sense. And you can do that by, for example, take one piece which happened to be Hamiltonian vector field, or symplectic vector field in this case, and then use this to take care of the rest, to kill the rest. Okay? And you kind of, the condition would be I V0 alpha 0 plus 1/2 sum j from 1 to k of d I Vj, no, there's no d here, d I Vj alpha 0 equals 0. So if you know what Vj's are, you know how much this thing is, this one form, and you want to match this, you want to choose V0 hat, the corrector, so that this thing vanishes. You know, that would kill the other. And since this guy is non-degenerate, such thing is possible. That's one way to construct it. Okay. The other one that actually is going to be relevant for Navier-Stokes equation would be this. I'm going to choose a diffusion that its drift is already Hamiltonian. However, the diffusion is not given in the Stratonovich sense. It's given in Ito sense. Okay, so let's look at this. Of course, if they were given a Stratonovich sense, then in order to make this symplectic, I have to make all these guys symplectic, which is not desired. I want to have a kind of more flexible situation. So under what conditions on Vj? So now V0 is fixed. And I want to kind of cook up a family of Vj that would make this weakly symplectic. And the condition can be written. You can easily formulate, work this out to see what conditions you get. And the condition would look like this. So since I don't have time, maybe I just say that you can easily write down conditions for Vj to guarantee this is symplectic. So we can work out conditions on Vj's to have X weakly symplectic. So let me tell you what application I have in mind in the case of Navier-Stokes equation. Application for Navier-Stokes equation. Okay. So you see, in the case of the Euler equation, I started with the Hamiltonian system, and I wonder whether I can find a function u on which the solutions to the Hamiltonian system lie. And I figured out that for such u, I need to satisfy Euler equation. Now I want to play a different game, namely, I want to look at this equation. So let's save time. So let's call star. So consider star with x equals q and p, but I want to kind of cook up a condition that would guarantee such that solutions lie on the graph of u, i.e. pt equals to u qtt, and the q part of the equation, you remember that you reduce the by saying p equals u of q, then you reduce the system to a system that involves q only. And the system for q becomes dq equals u qt dt plus a Brownian motion. So this is the Lagrangian way of formulating Navier-Stokes equation. So my condition is that this x will satisfy a diffusion that is weakly symplectic, and the solution lies on a graph function u, and then the q part would look like this. Namely, you have a very simple dependence on Brownian motion. The answer is that u must satisfy backward Navier-Stokes equation, namely ut plus uqu plus gradient p plus Laplacian of u equals 0. Backward because Laplacian on the wrong side. So to solve this PDE, you have to solve it for a final value condition. I'm going to switch to forward soon. Navier-Stokes equation. Okay, so if that is the case, then I already know that the flow of this produce all these forms that are in average sense are symplectic. But I want to know, what does it mean? Moreover, somebody in average sense is symplectic. Moreover, somebody is going to be a martingale. If I want to translate in this language, so the form, the standard 2 form, you evolve it with the flow of this diffusion, evolve the standard 2 form by this diffusion, and the result would not be conserved, would not be invariant with respect to time, but it's going to be symplectic, it's going to be a martingale. So when you work it out, moreover, if x denotes the flow of this equation, and A is x inverse, then if you look at dA, the derivative of A, say evaluated at A times t, and then if you look at psi, this is the vorticity. Psi evaluated at AAT t, if you call this MTA, this is a martingale. Of course, here I always have to assume that this is divergence free, otherwise what I'm saying is not true. So if you use a solution to Navier-Stokes equation, backward Navier-Stokes equation, and if you look at this vorticity and this kind of random flow, then you can produce a martingale involving this guy. And so that was backward. You can easily switch to the forward Navier-Stokes equation by change of variable. So replace u with negative u t minus t to go from forward to backward, and b hat t, the Brownian motion, you can kind of change variable and go backward. The outcome would be another Brownian motion. If you use this in a stochastic calculus, we know that the flow, the resulting flow, would be the inverse of the old flow. This is a formula of what's his name? I think Tanaka. And so we already know that in a stochastic calculus. So if you use that, then if you satisfies forward Navier-Stokes equation, then instead of this, I'm going to have a different thing. Namely, you can produce a new martingale, which is now dx at times psi x psi a t minus t, t between 0 and t. This is going to be a martingale. So you produce a martingale for Navier-Stokes here. So, you know, but where the formula of Constantin and Iyer stands, it turns out we know that martingale, the expected value doesn't depend on time. So if you set the expected value of this at time uppercase t equals to expected value at time 0, then you have the formula that was discovered by Iyer and Constantin. So in particular, so let me just finish it by saying that in particular, m at time 0 is the same as m at time 0 is the same as expected value. M0 is not, if t equals 0, let me see, if t equals 0, then this is still random. So the expected value of em0 equals to mt m at time t is not random because t equals t, that would be psi. Psi is not random. That's the solution to Navier-Stokes equation. And t, let me see. No, I think I'm making a mistake. Actually, I prepared notes. Maybe I use my notes. But where did I put my, oh, here. Maybe I didn't write it right. Let me see. Maybe I didn't write this correctly. Somewhere here. Okay. dx, okay, that was my mistake. This is correct. And so by setting, let me first for now say the expected value of m0 equals the expected value of mt, which is true for any martingale, then we get means that, okay, so let's see, if I put uppercase T here, then I'm going to get the initial vorticity. So I have psi 0. And this becomes the flow at time t. So expected value of this equals to, but if I put t equals 0 here, this would be identity, and I get the vorticity at later time. So, but that's no longer random because vorticity satisfies the deterministic equation. It's the flow that is random. X and A are random, but psi is not random. Psi is simply, you take the solution to Navier-Stokes equation and calculate this curve. So you get that psi at time t, this equals to that. This is a formula that was derived by Iyer and Constantin with a completely different proof. Maybe there is E here, I forgot. So the message is that if you use stochastic calculus by searching for symplectic, nearly symplectic diffusions, then not only you derive this, but also you show that this process, as t varies, is a martingale. So I think that would take care of half of the thing I wanted to say in this talk. But I guess for the other half, maybe another trip to IAS perhaps would do the job. So maybe I stop here.
Any question?
So does this interpretation help? For example, if you want to study regularity of the Euler equation?
That's a very good question. You know, I went through this with this hope that I can understand Navier-Stokes better, because you know I know some probability, and you know I know some symplectic geometry. My hope is to have a better understanding for Navier-Stokes and Euler equation using symplectic geometry. There's no doubt about it. But I can't answer that question now. What Iyer and Constantin did after deriving this and the similar equation without expected value, that's Weber formulation, they reprove all the things you know for Navier-Stokes, like the existence, the local existence of solution and regularity using this formulation. So they want to say that perhaps this formulation is as good or even better, you know. So some work in that direction has been done, but no new result. Let's put it this way.
So for this new formulation, you see you can predict better whether there's a singularity for Navier-Stokes equation?
So of course that would be an ideal thing to look for, but I don't have the answer. You know, I don't know the answer. My hope is with this formulation I have a better chance to understand what's going on, but I don't know the answer. So any new formulation, Navier-Stokes equation, of course, is welcome, because there are so many long-standing open problems in that area. My hope is using symplectic geometry. You see, there is all they have is just local regularity. I mean, I'm referring to the work of Iyer and Constantin, but just meaning that if for short time, if you solve the regular solution, for short time you can construct a solution which is as regular as the one you started initially for both Navier-Stokes and Euler. But this is not new. You know, we knew that before. So the answer is no. I mean, I don't know of any new regularity you can do it this way.
No more question? So what's that? Thanks, speaker again.